Welcome. Our goal today is to try to find a clever way to add up the counting numbers from 1 through n. If you have a small number of these to do, it makes good sense to go ahead and just add them up manually, maybe in order. But if you have a large pile of these to add together, then a different strategy would be really handy. And this stems from the handshake problem that we have already taken a look at. If you have a lot of people in a room and you have to add up all of those handshakes, then we would like a clever way to get at that. And here are a couple ways. So let's take a look at a shortened version of this. Let's pretend for a moment that we just need to do 1 plus 2 plus 3 plus 4 plus 5 plus 6. We're adding up the counting numbers 1 through 6. And if you did this by hand, you'd get 3, 6, 10, 15, 21. Okay, you could just do it by hand. But if we wanted to start looking for a more clever way of getting at this, something that could extend into larger numbers that would be handy for us to use, then here's a thought. And I don't expect that you would have come up with this on your own necessarily, so don't worry about that. Let's take this exact same list and write it underneath that first line, but let's write it backward. 6 plus 5 plus 4 plus 3 plus 2 plus 1. Those two sums would be exactly the same. And now look what happens. Let's add these two together vertically. 1 plus 6 will give you 7. 2 plus 5 will give you 7. 3 plus 4 will give you 7. 4 plus 3 will give you 7. 5 plus 2 will give you 7, and 6 plus 1 will give you 7. So you'd have 1, 2, 3, 4, 5, 6 sets of 7. 6 sets of 7 is found with multiplication. And because you had 2 rows of this happening, that's twice as much as you want. So take that and divide it by 2. 6 times 7 is 42, and divide by 2 is 21. And that's what we got when we added things together by hand. So how does this extend to something with n entries in it? Well, let's go back to that. And in that case, when we write this list backward, we'd have 1. This would be 2. We'll keep going backward. Way over here will be n. This will be n minus 1. And I know it looks a little bit strange with all of the algebra. But when we do this one, and we line things up so that we can find all of these sums, you will have a collection of 1, 2, 3, 4, 5, all the way to n sets, so n times. Each of these vertical sums will be n plus 1. This is n minus 1 plus another 2. That works out to n plus 1. And you can check it for the others. This will be n plus 1. This one would have been n minus 1 here, so n minus 1 plus 2 will also be n plus 1. We'll have n sets of n plus 1. And that's 2 rows instead of just 1, so we need to cut that final result in half. So this is the generic formula for the sum of the first n counting numbers, and this is one kind of visual representation of how that would work. So let's see if it works on 6. Let's take this rule and go apply it to the top number of 6. This would say that we would need to use 6, and then 6 plus 1, and then divide it by 2. And if you look at this for a little bit, you'll realize, oh, it exactly matches what we did before. 6 times 7, and then divide by 2. So that's one way to get at the sum of the first n counting numbers. If we try it in a more geometric method, let's try something kind of small here as well. Let's do the numbers 1 through 5 only. So rather than getting to this just yet, we'll do 1 plus 2 plus 3 plus 4 plus 5. And I'm only shortening it because of how many squares I have available. So to make this one work with a more geometric perspective, let's make pretend like you're shading in squares on grids. So here's 1, here's 2, 3 squares, 4 squares, and then 5 squares. And if you wanted to know the total, you could just count up all of your squares, and it doesn't seem like that is helping us make progress in any way. But then what we do is we realize, oh, this is kind of triangular, and we make its mirror image. So we're going to take this first triangle and invert it. Here's 1 square, 2, 3 squares, 4 squares, 5 squares. Kind of like the last time, we're starting to see that, oh, we have 1, 2, 3, 4, 5 squares vertically. When we come horizontally, we have 1, 2, 3, 4, 5, 6. And this makes a rectangle for us. The area of a rectangle is base times height. So this would be 5 times 6, but we only want half the rectangle. We only want the first half that we drew. So 5 times 6 divided by 2 would be the sum of these first 5 counting numbers. That is 15. We can go back and check and see if it works. 1 plus 2 is 3, 3 plus 3 is 6, plus another 4 is 10, plus another 5 is 15. So how would this work with a generic number like n, instead of capping things at 5? Well, we draw our first triangle in to give us our height in our rectangle. That's our n value. The second triangle comes along and makes the base, or helps us make the base of our rectangle. And to do that, we need 1 extra square on there, on that right-hand edge. So that's n plus 1. The area for a generic rectangle would be n times n plus 1, and that's twice as much as we need. And so we end up dividing by 2 to get the area that we need. And if you pop back to the other page, that is exactly the same formula that we had over there. This one is a more numerical version or algebraic version, I think. And then this one is more of a picture version of the proof. So if you want to find the sum of the first n counting numbers, you don't need to do them all one by one. You can apply this formula. And if you can envision one of these proofs for why it works, I think that that will go better for you. Let's come back over here where I have some space, and let's say that we have, let's say we have 80 people in a room, and we want to know the total number of handshakes. That would need to occur if each person shakes hands with each other person in the room exactly 1 time. This was the handshake problem. So to do this one, we can find an answer this time. The first person, I don't care who the first person is, but find a first person. They will need to come along and shake 79 other people's hands, and then they're out of the running. And then the next person shakes 78 hands. And this goes on and on until we're down to 4 plus 3 plus 2 plus 1, all of them added together to help us find the total. So this is the sum of the first 79 counting numbers. To find this sum, we would need to do 79 times 80 divide by 2. So you can think of this as reorganizing this sum by putting the 1 under here. That would give us 1 plus 2 plus 3 plus 4 all the way along. That would give us vertical totals of 80, and there'd be 79 sets of them, but that's twice as much as we need. You can also think of this as making the triangle, where first it's 79 units tall, and then it's 80 units wide, 79 and 80, and that's twice as much as you need, so divide by 2. And then you need to figure out this total. A calculator might be handy for you here. 3,160 handshakes altogether. And I think you can agree that you do not want to type these into your calculator individually, and you probably don't want to add these up by hand either. If you're interested, there's an interesting tale about the mathematician Carl Friedrich Gauss from when he was little, and one of his elementary school teachers set him to a task something like this, thinking that it would take him hours and hours to do and keep him from bothering her. I think you should look that up. It's kind of interesting. All right, this is enough. You can now find the sum of the first n counting numbers.